Let us go ahead and continue the discussion on HD44780. In this session, we'll be speaking about displaying custom characters and then resetting the graphics controller and initializing it. Now, before we go ahead and display a custom character on the LCD panel, that character needs to be stored in the custom graphics RAM or the CG RAM. Now CG RAM in HD44780 is of 64 bytes. Now each custom character requires 8 bytes. So as you could calculate, so this is 64 bytes divided by 8 bytes per character gives us number of characters to be 8. So we have 64 bytes of CG RAM, and each character to display each custom character, it takes 8 bytes, and thus we can display 8 characters, or we can store 8 characters in the CG RAM. Now we'll just draw a simple pattern and we'll see how 8 bytes are required. So say this, for example, say we have this 5x8 matrix. Okay, now 4 and 5. So as you could see that there are 8 rows and each row corresponds to a byte. Now say for example we need to display, let's say we'll display a battery. Okay, so symbol for a battery, so it should be something like this. So all these dots or pixels should glow, and the ones that are gray, they are turned off. And say we want to show a battery full or battery half, and say we would increase its level, and then we want to show as the battery charges, we want to show battery charging up. So say we want to display this particular character on CG RAM. So to do that, as you said earlier, this pattern needs to be saved on the CG RAM. Now, so as you could see, this is D0, D1, D2, D3, D4, and D4. So D5, D6, and D7. So it stores data in chunk of 8 bits or a byte. So these 3 bytes should be don't care, so we'll assume them to be 0. So the pattern for this would be all zeros followed by 1 1 1 zeros, which is 0x 0e. The next would be so all ones, and if you assume this as this 3 as 0, it would be 1f in hex. So, and if we continue likewise, so these are again all zeros followed by 1, so this is 1 and 1, and again this would be 1 1 in hex. This would be 1 and 3, so 1 3, and then this would be what? So this is 0 0 0 1 and 7 0x 1 7. This would be all zeros 1 and f, so this is 1f and this is 0x1f. Now what you could see here is we have these 8 bytes, and these need to be stored in the memory. If you are using a cursor, you might just shift up and start displaying from here. Now, as we have seen before, the way we do this is we know the command to set the CGRAM address, and that would be, now since we are sending a command, register select would be 0, and read/write bar, since we are writing a command, this would be 0, and the command to write the starting address of DRAM is, so the bit D7 should be 0, and D6 if it is 1, then what follows from D5, D4, D3, D2, D1 and D0. I'm a little out of space here, let me just rewrite this. Okay, so this is D7, D6, D5, D4, D3, D2, D1 and D0. Yeah, great. So if D7 is 0, D6 is 1, and what follows in the command is the CGRAM address. Now, as you could guess, there are 6 bits to it, so 2 to the power 6 makes 64, and as we have discussed, there are 64 bytes. So if you want to store this character starting from the first address, then the command basically would be, so let me write it from D7, so it would be 0, 1 and all zeros. Now if we send this particular command to the LCD, making register select as 0, read write as 0, and if we send this particular command at the pulse of enable signal, then the the address pointer would point to the first location in the CGRAM, and what we next need to do is write data, and the command to write data is register select, in that case would be 1, and read/write would be again 0 because we are writing data, and what we would write is the first byte of our character, and which is 0E. So this is 0 and this is E. Now one good thing about this is we need not send this command every time. So whenever we wish to write 8 bytes so that it makes up a character, what we need to do is we need to send this command only once, and the address pointer, it automatically increments and points to the next address. So we can consecutively send all the hex pattern that we have written, so all the 8 bytes we can write. So with the command with making register select as 1 and then read write as 0 and then sending the first byte, it sets up it writes the first byte and then the address pointer increment. So we can consecutively send this command with the bytes as we have derived, or the byte pattern. So if we go ahead and do that, so the 8 bytes would be stored from addresses 00 in hex 207 in the DDRAM. So this is in the DDRAM. So this is where our first character gets stored. So the next character would get stored from 0x08 to 0x0f. Similarly, the 8th character would be in the last position. So 0xff would be the end of the last character, and 0xf8 would be start of the 8th character. So in this way we store all the 8 characters that are required. So every time you send a character, what needs to be followed is you need to set up the address. So for the first character it would be 0100 and register select read write should be 0, and then you consecutively send the 8 bytes. Similarly, for the second character, the address needs to be, so since we are we should write at 0x08. So the address would be, this should be 0, this bit should be 1, and this should be 8. So likewise we go ahead and write all the characters in the memory. Now how do we read the character that is stored in the memory? We'll just look at that. Before we do that, let me just clear this up. Now displaying the character is pretty simple. As we have discussed, if we send the data RAM addresses from 00 to 0F, the first 8, 00 to 08, in hex they will display custom characters 0 to 7. So our first character would be stored at location 0, and the 8th character would be stored at location 7. And if we go ahead from, so this should be 07, and if we start from 08 to 0F, again all these 7 characters would be repeated. You should have watched this in the last video. So to basically summarize, what we need to do is to display a custom character, first we need to make the binary pattern, which is 8 bytes, and then we need to store it in CGRAM. So for this the command would be, so for a command, register select would be 0, read write would be 0, and the command would be so this is basically D7 would be 0, this would be 1, and this would be followed by the address. So next 8 bytes would be address, 6 bits would be address. So say for first character, the command would be 0x40. So this is the starting command. So it sets the address in CGRAM, and then you consecutively write 8 bytes. And since we are writing data, register select would be 1 in this case, read / write bar would be 0, and then we write, and it auto increments, so we need not worry, we consecutively need to write 8 bytes. And to display a character, we simply need to write the data, and we need to send a command, like say you want to display custom character stored at location 0 on the CGRAM. To do that, we simply need to send ASCII value or 0, or we simply need to send 0 because that is where the first custom character is stored. So that would be, for that register select would be again, since we are writing data, it would be 1, and read / write bar would be, since again we are writing the first character, so this would be 0, and we need to send the ASCII value 00. So if you do that, the first character is displayed. Alright, now let us go ahead and look at the memory map. Now as you could see here, this is how it is stored. This is CGRAM. So these 3 bits are don't care, and this is pattern for character 1. Now what you could observe is the CGRAM addresses, they are they are 6 bits, so they start with 000 and 0, and this is 00111, which makes the first character. So these 8 combinations make first character, and then similarly this bit changes to 1, and the next is the next character. Similarly, this is the 7th. If we start from 0, this would be 7th character. So total 8 characters would be stored. Now to display, so if we send the DDRAM data as 0, first character would be displayed. Since this is don't care, even if we send this bit as 1, the same character would be displayed. You should have seen this video. The character repeats on position 0 and position 8. So similarly, we can store and read all the 8 characters. Now, before we go ahead and conclude this video, let us go ahead and see what it takes to initialize the LCD. And before we see that, why is it important to initialize the LCD? Now, if you are interfacing it with a high-speed microcontroller, or even say a controller which works between 10 to 20 megahertz, the controller boots up very fast, and if we write some initialization code on the LCD, the controller would execute that in a few milliseconds. But the LCD, as you would see in the next slide, it takes several milliseconds to boot up. So what happens is, before even the LCD boots up, the controller would have gone past the basic commands or basic data that we set, and this often results in LCD displaying garbage values. So in the next video we'll look at what the exact sequence for booting up the LCD would be. Now, as you could see, this is for 8-bit mode and this is for 4-bit mode. Now, what they recommend is to wait for more than 15 milliseconds when the LCD is powered up at 5 volts, and wait for more than 40 milliseconds when it is powered at 3 volts. So once the controller boots up, even before you send the first command, you should have wait, and the controller should wait for this time. So, and after it does that, we need to consecutively send the function set command for 3 times, and the LCD specifies it, and unless it is done, we do not have the busy flag available. So the busy flag, again we had missed it, so let me just cover that up. So busy flag, what basically it does is it tells us whether the LCD has finished displaying something, and to do that we need to read. Now if this is an MCU, we need to and if this is LCD, we need to read back from LCD, and since this is command which you are reading, so register select in this case would be command register, so this would be 0, and since we are reading from LCD, this would be 1. Now what it returns is on D7 to D0. Now D7 is important in this. D7 is the busy flag. If LCD has finished displaying the previous character or the previous command that we have sent, if it has finished executing that, the busy flag would be 0. Otherwise, if it is busy doing its task, the busy flag would be 1. Now this is very important when you do not want to give delay between commands, and you want to actively read when the LCD is free, and then you want to send the next command. The busy flags plays an important role, and for the busy flag to be available, we need to do this function set, and once we send this command, we need to wait for 4.1 milliseconds and then 100 milliseconds, and again if we send this command, which is basically 0x30 for the 8-bit mode, if we do this, and even for the 4-bit mode, so if we do this, then the busy flag is available from this point onwards. Now after you do that, then we do the normal sequence for booting up the LCD. So what that includes is we do the function set command as discussed earlier. So the function set command, it tells us the number of lines the display has, the font size, and all of that. And for the 8-bit mode, this would be 1. This bit would be 1. So this is D/LNF. So, and this we have discussed previously. So we have to set the command. So this basically sets the interface length, which is 8 bytes, all the 8 lines, D7 to D0. Then it will set number of lines and the font size 5x8 or 5x10. Then we turn on the display, so this becomes 1, cursor becomes 1. If you want the cursor to be blinking, this becomes 1. So we send the display on off command, then we clear the display, and then we set the entry mode. So entry mode basically the normal one as discussed previously, increment decrement, so it should increment, so this becomes 0 and this becomes 0. So what it does is it displays a character, and then the DRAM content, it is incremented. So if you display the next character, it goes on to the next position on the LCD. So this is how we do for the 8-bit mode. Now for the 4-bit mode, it's similar. So only thing you could observe is B4 to B7, only B4 to B7 or D4 to D7, only the 4 data lines are connected. So again we do the same thing. We send the function set for 3 times, and then we set the 4-bit mode with this command. Now what you could observe is for the commands that require 8 bits or a complete byte, what we do is we split the command into 2 nibbles. So this is the higher nibble and this is the lower nibble. So we send the higher nibble first, and then we send the lower nibble. So similarly we do the function set display on off, the clear LCD, clear display command, and we set the entry mode. Thank you for watching. We will be using all this to build a software library for all of the major controllers. So stay tuned for more.